let's say instead of that, I picked sine. So let's say S of t is equal to S prime of t, my modulated signal, is equal to S of t sine 2 pi f c t. And then I demodulate with sine. Or excuse me, I down convert using sine, not cos. We should get much the same answer. So what I'm going to do is I have S of t sine 2 pi f c t. And I'm going to multiply by 2 sine 2 pi f c t. What I get out is S of t, 2s of t sine squared 2 pi f c t. And what is sine squared? Does anybody know this identity? Anybody?
1 minus cos 2x
Over 1 minus cos,
over 2.
yeah, 2 pi. Yeah, excuse me, that should be f d. Oh, this should all be in the, sorry, this should all be in discrete time. S of k sine 2 pi f dk. That's 2 sine 2 pi f dk. And that's 2 S of k sine 2 pi f dk. So sine squared, excuse me, 2 S of k sine squared 2 pi, let me back up. Just doing the identity by itself, sine squared 2 pi f dk is 1 minus cos 2 pi 2 f dk divided by 2. And what I end up with is 2 S of k 1 minus cos 2 pi 2 f dk divided by 2 is equal to that 2 cancels with this 2. I get S of k minus S of k cos 2 pi 2 f dk. And then again, low pass filtering will reject this term, and I end up with the original signal. So in other words, if as long as I'm consistent, I can use either sine, or if I use sine and sine, or cos and cos, either way I extract the baseband signal. Okay. Any questions on that? Now, what happens if we are not consistent? So, my signal, let's say my signal I use sine, except my demodulator I use cos. On my down conversion, excuse me, I use cos. So, I end up with 2 S of k sine 2 pi f dk cos 2 pi f dk. So what is sine x cos x? I can express that in terms of a single sinusoid. Anybody know how? It's 1/2 sine 2x. So this ends up being 2 S of k sine 2 pi 2 f dk. So what happens after I low pass filter that? So now, what did I do? Now there's no baseband component, and there's stuff out here at minus 2FD and plus 2FD, because that's what I did here. I'm multiplying the original baseband signal by by this sinusoid. So if I low pass filter, what do I end up with? Nothing. So it should be clear that if I have S of k cos and sine on the down conversion, I get the same expression here, so the same result now. So in other words, let me put back my my hardware model for the digital down conversion. So if I have sk cos 2 pi fdk, then what do I get? Over here I get s of k, and over here I get 0. On the other hand, if I have s of k times sine 2 pi fdk, what do I get? What do I get from this leg? 0. And from this leg, s of k. So, anyone suggest a way to send two signals at once? So here's what I'd like. I'd like S1 of k and S2 of k. So those two signals are different. How would I do that?
So as alpha sine equals what now plus.
Right. Exactly. So I want to get S1 of k out here. So let's send that on the cos carrier. So if that happens, what'll I get? I'll get S1 out here and 0 out here. And I want S2 over here. So what'll I do? I'll modulate that with the sine carrier. So what'll happen there is I'll get S2 here and 0 here. Everything here is linear. These multiplications, they distribute over the addition, and the low-pass filters are linear. So in the end, I get S1 of k plus 0 and S2 of k plus 0, which is exactly what I want. So we can send two signals, two arbitrary signals at the same time. What we do is we send S1 k cos 2 pi f dk plus S2 k sine 2 pi f dk, and then S1 is captured by the in-phase leg of the digital down converter, and S2 is captured by the quadrature leg. This is the in-phase leg up here, and this is the quadrature down here. In fact, you may as well call this SI for in-phase, and this